Welcome back to the HFWorks video series. The effects of tuning screws depth on the S parameters of a 5G bandpass filter. At a 5G frequency of 29 GHz, the wavelength is around 10.33 mm. 1 mm is basically lambda over 10. As a result, the passing properties of the filter are expected to be sensitive to the screw's mechanical penetration. To study such sensitivity, we chose the popular EMWorks' high-frequency simulator, HFWorks. Since HFWorks is an add-in to SolidWorks, the #1 3D CAD software, the creation and modification of the filter is as easy as a pie. Therefore, we skip the geometry creation part and dive straight into HFWorks. To achieve our goal, the parametrization feature of HFWorks is used. To add a new study, right-click on the project name and choose S parameters. In the General Properties tab, check Parameterization. Click on the Frequency Sweep tab. Enter 27 GHz for the start frequency and 29 GHz for the end frequency. Enter 100 for the number of frequency points. Click on the Meshing tab. Choose Adaptive Meshing and accept all the defaults. Click OK. A new parametric study is added to the HFWorks Manager tree. Click back on the SolidWorks Feature Manager design tree. Define 4 global variables H1, H2, H3, and H4 that represent the depth of the screws. If you do not know how to create global variables in SolidWorks, please refer to the SolidWorks help. Click again on the HFWorks Manager tab. Right-click on the project name at the root of the HFWorks Manager tree and choose Parameters. Import the global variables from SolidWorks and check OK. Right-click on Design Scenarios and choose Edit Definition. For parameter type, choose Range with steps for all the variables. Specify the minimum, maximum, and step for each variable and generate scenarios. Click OK. The scenarios are now created. Let's apply the material for each body. Click on the plus sign next to Filter. Right-click on Air Body to apply air. Right-click on Enclosure Body to apply copper. Right-click on Screws part that has several bodies to apply materials and choose Stainless Steel to all bodies. Consequently, the screws are stainless steel, the cavity is air, and the metallic enclosure is copper. Let's apply the necessary boundary conditions. The metallic boundary conditions are implicitly applied through the materials. They are referred to in the material tree items as implicit IEC. We are left only with the port's boundary conditions. Click on Boundary Conditions and choose Port. Apply port 1 on the rectangular face of air cavity. Click on Boundary Conditions and choose Port. Apply port 2 on the opposite rectangular face of air cavity. All the pre-processing is now complete and we are ready to run the parametric study. Right-click on the study name and choose Run. Of course, it would take some time to run it. Let's instead examine an existing study that was run previously. There are field and circuit parameters results. To show the fringe plot of the electric field, just click on the electric field icon. The magnitude of the electric field is color-coded, where the red color is the maximum and the blue color is the minimum, as shown on the legend on the right side of the plot. You can also slice the plot to look inside the model. Right-click on the section plot and choose Clipping. Click OK. You can animate versus time, scenarios, and section cuts. Scroll down and choose Animate versus Scenario. You can see how the electric field distribution varies as function of the scenarios. You can also animate the different section cuts for a given scenario. Scroll down again and choose Animate versus Section Cut. HFWorks automatically makes many section cuts and animate them. If the animation is too fast, you can slow it down by moving to the left. You can also examine the circuit parameters results table. Double-click on the results table. You can examine the scattering parameters, the admittance, the impedance, and the port results at all frequencies and all scenarios. You can print or export the results for various formats. Click Close. Under the Plots folder, double-click on Plot 1. The S11 versus frequency for all the scenarios appears. As you can see, the S11 heavily depends on the screw's depth. You can also examine the listing of the data for all scenarios. You can export the data to various formats. You can add a new plot by choosing 2D plots. Scroll down and choose S12 in all scenarios. Click Add. The plot of S12 versus frequency appears. Again, the S12 heavily depends on the screw's depth. Last but not least, you can generate a report for the entire study that contains all the pre- and post-processing results. To generate a report, right-click on the Reports folder and choose Generate. Customize your report by choosing the logo, author name, company name. Choose either HTML or Microsoft Word format. Click OK. The generation of the report starts. The time to generate the report depends on the amount of data. You can now conveniently examine the report as it is organized by section. You may click on a section to jump to it directly. Of course, you can print it, save it as a PDF file, or even share it with co-workers on the web. We can, therefore, confirm that for a 5G tunable bandpass filter, the depth of the screws is very critical. A tool like HFWorks is indispensable to design and optimize 5G type filters. HFWorks will help you save time and money by virtually prototyping your 5G design. Thank you for watching and bye now.